I'm just going to start. I wanted to thank the organizers, not just for the whole conference, but special thanks because the schedule was rearranged so that I, Rob DeSalle, and Michael Friedman could go consecutively. We, together with Craig Fox, who is not here at the moment, are preparing a book called Newtonian Relativity, which we are dedicating to Howard and hoping that some of his papers on Newtonian space-time, etc., will appear in it. He would have heard that if he were here today, and I had saved that for this occasion. But unfortunately, he's not. Well, he will hear it. He will hear it on the recording. Among those papers is the one I'm citing here, which is a little less well-known. In it, Howard highlighted a lacuna in Newton's derivation of his law of gravity from phenomena, argued that it was filled by Newton's metaphysics of interaction, and then proposed that the whole of Book 3 should be viewed as offering the deduction of the law. I happen to be chair of the PSA session where he presented the paper, still early in my efforts on Newton. Howard convinced me to focus on the whole of Book 3, and when I found much of the evidence in Book 3 rather problematic, I then turned to focusing on the evidence for Newtonian gravity over the course of the subsequent history of celestial mechanics, for which I guess I'm best known. With apologies to those who don't really give a damn about the details of Newton's reasoning, and I suspect that's about half of this room or more, I'm going to be, as I say, offering manuscript evidence for a conjecture Howard made in ending his paper. And when I prepared this, I certainly thought I was delivering it to Howard, and all the rest of you were simply eavesdropping. Since he's not here, that's not going to work, and I apologize. So Newton derives the numerator of his law in Propositions 6 and 7. Proposition 6 appeals first to experiments he's done and then to celestial phenomena to conclude that the force of gravity is proportional to the mass of each body on which it acts, or in other words, that gravity, unlike other forces, has the same effect on all bodies at any given point. Proposition 7 then completes the numerator by inferring from the conclusion that gravity is proportional to the mass of the attracted body, that it is proportional as well to the mass of the attracting body. The reasoning in Proposition 7, however, presupposes that Newton's third law of motion holds for gravity, a claim for which he has to this point offered no evidence. Indeed, he simply stated it, buried in a subordinate clause in the first corollary of Proposition 5, which, by the way, in the third edition, he finally dropped the parentheses around that. As Howard pointed out in a footnote in his article, Roger Coates, the editor of the second edition, called Newton's attention to the lacuna upon receiving the text in which Newton claimed he feigns no hypotheses. I didn't include it in the quote, but Coates goes on to propose that Newton dropped the feign no hypotheses claim. Newton's reply somewhat begs the question by invoking a thought experiment in the scholium to his laws of motion that concludes the third law must hold for mutual attractions between bodies that are touching one another. Some have gone so far as to suggest that Newton had been unaware of the lacuna before Coates called his attention to it. If nothing else, I'm going to show that this is false, that Newton was aware of it even before the Principia had begun to take shape. My point now is that Coates put his finger on the lacuna. Where is the evidence that the third law holds for gravity between bodies that far removed from one another, like Jupiter and the Sun? Howard appears to have been unaware of a remark by Euler, rather outspoken remark 25 years after Newton died, that no phenomenon had yet shown that the attractive forces of the heavenly bodies are proportional to their masses, noting that Newton's values for the masses presupposed his law of gravity. The further remark that taking the third law of motion to hold for celestial gravity is a crude hypothesis is even more striking insofar as Euler was the chief champion and master of Newtonian celestial mechanics at the time. Euler was more than right, by the way. In any system of non-contiguous bodies in which the only force is gravity, no phenomenon of motion can ever show that gravitational attraction toward a body is proportional to its inertial mass. Indeed, no phenomenon can serve to measure the inertial masses of any of the bodies in such a system, precisely because, in keeping with Proposition 6, the response of any body in the system to a gravitational force is always independent of its mass. The question is when Newton first realized this. I'm going to claim very early in 1685, if not before. In his 1990 paper, Howard, in his rather characteristic manner, made clear exactly what the lacuna is. Quoting, "But the third law of motion does not tell us that whenever one body is urged by a force directed towards a second, that second body experiences an equal force towards the first. It tells us rather that whenever one body is acted upon by a second, the second body is subject to a force equal in magnitude and opposite in direction. The question Newton was begging is whether and how gravity can act on bodies at a distance, and hence it was, again quoting Howard, far-fetched to apply the third law of to gravity in the fashion Newton did. Howard then argued the engine that drives the enormous step to the law of universal gravitation is a certain conception of the character of a force of nature or natural power such as gravitation, namely that a force of nature is a force of interaction, and that such a force is characterized by a law of interaction, a law in which the interacting bodies enter altogether symmetrically." And then at the end of the whole paper, Howard conjectured, quote, "that this whole conception of the constitutional frame of nature was actually developed by Newton at the same time as he was discovering his law of gravity." I think Howard was not only right about this, but that the time in question was at the latest very early in 1685. A few years ago, Rob DeSalle asked me about the manuscript history of Corollary 6 of the Laws of Motion. Where is he? Something that's changed my life a good deal, that innocent question, because it's consumed a huge amount of my time since then. That's the corollary that identifies conditions under which the whole of our solar system, for example, could be moving in any way whatever without affecting the motions of the bodies in it among themselves. This led me to go back to the original manuscripts between the November 1684 registered version of De Motu and the manuscript of Book 1 Newton sent to London in April 1686. Only one of the manuscripts from 1685 is complete, Liber Secundus, later cited by Newton as the original version of his System of the World, written in popular form. What popular form meant was the exact same format as Descartes' Principia, articles with postals in the margin. My postals won't be in the margin, they'll be at the top of each article. But it looks exactly like Descartes' Principia, or was intended to. Latin and English editions of it were published shortly after Newton died, but unfortunately the editors made changes to make it look far more contemporaneous with Book 3 of the Principia than it actually was. More importantly, they ignored all the revisions Newton made to it while it was being composed. These revisions, especially shifts to new technical wording, provide a basis for the sequencing of the manuscripts shown here. Only one of the manuscripts from 1685 is in Newton's hand, but deletions and insertions always are. As you can see, only 4 dates can be pinned down, yet save for a couple of questions of overlap, the sequence itself can be. Starting from work of Anne Whitman from back in the 1970s, she died in 1984, I've prepared a full variorum translation of Liber Secundus, as well as of the portions pertinent to it of the other manuscripts up here. The rest of the talk is going to be based on these translations, starting with the irregularly yielding media fragment. In the first place, it's the first place that Newton mentions an experiment to verify that terrestrial gravity produces the same acceleration in all bodies, and hence the quantity of matter in them is proportional to their weight. Or as Newton said in the initial manuscript, it's usually proportional to its gravity. Don't ask me what he thought the exception was. On the verso side of the first folio, Newton introduced for the first time a single word, pondus, for the quantity of matter moved, a word that he replaced with massa, mass, late in 1685. For those who don't know, pondus means weight. The little caps in red indicate insertions. The 5 insertions in this short passage are typical of Newton drafts. The important point to notice is that the experiment proposed to verify the claim in the initial manuscript has now been carried out, justifying the introduction of a new quantity labeled pondus by virtue of a measure that assigns it determinate values. I'll come back to this experiment in a moment. Now for Liber Secundus. First, I have to call attention to a difference between it and the Principia. In the Principia, Newton, Proposition 6 starts with the 2 pendulum experiment in terrestrial gravity and then turns to celestial gravity. He does just the opposite in Liber Secundus, where the celestial case comes first in Article 18, followed by the terrestrial in Article 19. Let me quote the first part of the conclusion and then go back to what the argument is. Quote, "At equal distances, therefore, there is an equal action of centripetal force upon all the planets in proportion to their bodies or quantities of matter in the bodies." 2 phenomena are cited from which this conclusion is drawn. Kepler's 3/2 power rule holding for the planets, and the motions of the satellites of Jupiter being so regular. Notice that Newton first used the word pondus throughout the article, but then seems to have found the ambiguity resulting from the same word to mean both weight and quantity of matter a problem, and gone back and replaced pondus everywhere it meant quantity of matter. This, of course, places this article after he had inserted the new definition of pondus, as shown on the slide before. That he presented the celestial case first and then the terrestrial case with the 2 pendulum experiment after it raises a question. Might he have come upon this half of the numerator of his law of gravity first from the celestial considerations he cites, and only then turn to Galileo's claim for the terrestrial case, deciding finally to carry out the experiment to make sure of Galileo's claim? The answer is yes, I think. Not only that he might have, but he almost certainly did do the celestial case first. Okay. For in problem 4 of the original De Motu tract, he had already taken for granted that at equal distances there is an equal action of centripetal force on all the planets in proportion to their quantity of matter. Partly because the scholium extends the solution to comets, but even more so because of a tendency to read it from the perspective of the Principia, and not from that at the time it was written, the extraordinary character of this solution to the initial value problem has gone unnoticed. I wish Howard were here for this. Under the assumption of an inverse square variation of force with distance, all that is needed to give the quantity of force everywhere around a center is a single orbiting body. For the motion of any other body can be obtained by simple ratio off of this one by virtue of the cube of the mean distances being proportional to the square of the periods. But look, one can extrapolate from one orbiting body to another only if the quantities of matter in them make no difference. Or as the slide says, given one body in orbit around a center toward which there is an inverse square accelerative tendency, the magnitude of that tendency is known everywhere else. The one comet Newton had studied extensively, the comet of 1680-81, had an angle of inclination of 60 degrees with respect to the ecliptic. So the problem is taking the inverse square accelerative tendency to fill the space surrounding the center, or in Howard's words, an acceleration field. But this still understates how extraordinary problem 4 is. What it shows is that given an inverse square tendency toward a center that's the same at each point for all bodies, all that's needed to fully quantify motion in response to this tendency is a single body in orbit around the center. If the masses of the body made any difference, they too would be required to fully quantify the situation. Now, I do mean fully quantify, as the proof goes on to reveal all sorts of counterfactual claims can be run off this solution. For example, what would the velocity have to be at a given point for the body to describe a parabola or a hyperbola or an ellipse of some other eccentricity? We should never lose sight of how important such quantification was to Newton. The quote here is from the early 1670s, but with a slight change in subject from optics to mechanics, it could have served as an epigraph for his Principia. I hope to show how valuable mathematics is in natural philosophy. Going on, instead of the conjectures and probabilities that are being blazoned about everywhere, we shall finally achieve a science of nature supported by the greatest evidence. A couple of years after the Principia appeared, Leibniz published his essay on the causes of celestial motions. Its scope is more or less that of the first half of the original De Motu tract, 3 or 4 pages. Where it stops, where Leibniz's theory ceases to be able to do even a semblance of what's in De Motu, is with problem 4. Neither Leibniz's vortex theory nor Johann Bernoulli's 40 years later were sufficiently quantified to have any way at all of addressing the initial value problem. Newton's having a solution for it already in 1684 was truly remarkable. So by late 1684, Newton had seen that the way he was using Kepler's 3/2 power rule requires all bodies at any point to respond to the centripetal forces toward the sun in precisely the same way, regardless of their respective quantities of matter. When he also realized that the regularity of the motions of Jupiter's satellites implies this too is not so clear. In a letter at the end of 1684, Flamsteed noted the strangeness of the moon's motion being, quote, so perplexed with inequalities, and the motions of the satellites of Jupiter being, quote, so free of them. This seems to have caught Newton's attention. For some time before he had gotten very far into Liber Secundus, he added a proposition to Liber Primus that he numbered 35, and then 21 corollaries to the next proposition, renumbering it as 36. All those corollaries are on perturbations produced in a system of orbiting bodies by a force from outside of it. Corollaries 14 through 17 provide a quantitatively precise explanation for the contrast Flamsteed had noted, taking full advantage of the respective strengths of the centripetal tendencies toward the Sun and Jupiter, defined by the respective 3/2 power proportions. These corollaries presuppose that the centripetal tendencies toward both Sun and Jupiter are the same for all bodies, regardless of their quantities of matter. So Newton certainly saw how the regularity of the motions of Jupiter's satellites provides evidence for the conclusion during the first quarter or so of 1685. But then we have a manuscript that he saw it before then. For consider proposition 3 at the very beginning of Liber Primus. Every body which by a radius drawn to another body is center, moving in any way whatsoever, describes areas proportional to the times, is urged by a force compounded of the centripetal force tending toward the other body, and of the force by which the second body is in proportion to its bulk, urged. So this proposition, which together with its second corollary licenses treating the system of Jupiter and its satellites as quasi-insular, is already invoking forces that vary in proportion to the quantity, bulk or quantity of matter in the bodies on which they act. Notice that the proof cites corollary 6 of the laws of motion. Treating the Jupiter system as quasi-insular is most likely the reason Newton added corollary 6 in the first place. But if corollary 6, expressed as it was then expressed, said as it was, however it was then expressed, because the vocabulary he finally used didn't exist at this point, if it was already present when Newton embarked on Liber Primus, so too were corollaries 2 and 3. The former licensing the resolution of forces into arbitrary components, and the latter announcing for the first time anywhere the unqualified and universal conservation of what we now call momentum, which itself, in Howard's words, presupposes that forces in nature must be forces of interaction. Finally, notice that Newton does not yet have the word pondus, much less the word massa, available for the quantity of matter. So at least his decision to use pondus for this purpose, and not the two pendulum experiment as well, had to post-date proposition 3. The phrasing in the manuscripts thus gives us evidence that Newton came upon the conclusion that forces of gravity are proportional to the quantities of matter in the bodies on which they act, first from considering the celestial realm, and only then turn to the terrestrial. So let me now turn to Article 19. This is the terrestrial case, as you can see. The description of the two pendulum experiment was copied nearly word for word into the Principia, even to the point of including the adverb exacte, a word Newton almost never used in any edition of the Principia, even though he had used it throughout Liber Secundus, in conjunction with the adverbs accerate and quam proxime, to draw a threefold contrast. Notice that the article originally included an explanation for his use of the word pondus, later deleted. The point I really want you to consider, however, is how much entered into the experiment itself, which of course provided the first quantitative evidence ever for Galileo's claim. First was the very idea of verifying the claim with pendulum experiments. Then there was the authorizing theorem, not yet numbered. And finally, there was all the effort required in executing the experiment. This was not something for which Newton had the idea on waking up some morning and had pulled it off by nightfall. It had to take several days to devise, develop, and carry out. When did he manage the time to do this? All we can say is before Liber Primus had reached proposition 38, where pondus, as you'll see, is used, but after proposition 3. Regardless, the manuscript evidence indicates that the half of the numerator of the law of gravity which Newton could legitimately be said to have derived from phenomena was in place early in 1684, if not before. I meant 1685, if not before. That's a mistake. But now consider how strange this half was. On the one hand, at every point, all bodies respond to the force of gravity in the same way, yet the forces required to prevent them from falling are not the same at all. They vary with the quantity of matter in the bodies. Moreover, in both Huygens' and Newton's solutions for the impact of perfectly elastic bodies, the resistance of each body to any change of its motion was said to be proportional to its bulk. Even further, Newton himself, in the registered version of De Motu, had said the deceleration of projectiles from air resistance is inversely proportional to their weights. And everyone knew that the tension in a sling varies with the weight of the body it's retaining. All of these cases involve forces from without, to use the phrasing of the principle of inertia in the version of De Motu that Newton had sent to London. So how does a force of gravity acting on a body from without manage to adjust its magnitude, or in Du Châtelet's wonderful phrasing, proportion itself to the quantity of matter of each body on which it happens to act? My claim is that Newton was not only fully cognizant of this question before he wrote Liber Secundus, but it was what compelled him into the view that, again in Howard's words, forces of nature are forces of interaction. And with this view, to add his third law of motion to the sequence of tracks of the De Motu tracks. My evidence for this begins with the very next article in Liber Secundus, quoting, "And since the action of centripetal force upon the attracted body at equal distances is proportional to the matter in this body, it is reasonable also to grant that it is proportional as well to the matter in the attracting body. For the action is mutual and causes the bodies by a mutual endeavor, by law 3, to approach each other, and accordingly the action in one body must necessarily be in conformity with the action in the other." Saying that it's reasonable to grant some claim is not quite the same thing as deriving it from phenomena. This is the first place that the third law of motion is cited in Liber Secundus, and hence nowhere before here has Newton offered any evidence that it holds for celestial centripetal forces. I'll come back to the third law in a moment. Let me go on to the very next article now, which Howard did quote in his paper, quoting sections that I've highlighted, "And hence it is that the attractive force is found in both bodies. The sun attracts or draws Jupiter and the other planets. Jupiter attracts or draws its satellites. And similarly, the satellites act on one another and on Jupiter, and on all the planets act on one another. And although in a pair of planets the action of each on the other can be distinguished and can be considered as paired actions by which each draws the other, yet inasmuch as these are actions between two bodies, they are not two, but a simple operation between two termini. There is not, for example, one operation by which the sun draws Jupiter and another operation by which Jupiter draws the sun, but a single operation by which the sun and Jupiter endeavor to approach each other. By the action by which the sun draws Jupiter, Jupiter and the sun endeavor to approach each other by law 3, and by the action by which Jupiter draws the sun, Jupiter and the sun endeavor to approach each other. Moreover, the sun is not attracted by a twofold action towards Jupiter, nor is Jupiter attracted by a twofold action towards the sun, but there is one action between them by which both approach each other. I hope all of you have read enough Newton to know he's very rarely that redundant in saying the same thing again and again. And then the conclusion, in this way conceive that a simple operation arising from the conspiring nature of two planets is exerted between them, then this operation will be the same with respect to both, and thus being proportional to the matter in one of them, will be proportional to the matter in the other. Nothing remotely akin to this paragraph ever appears in any edition of the Principia. Article 22 explains why we don't observe such mutual attraction among terrestrial bodies, because the force of gravity is too weak. This is followed by the article displayed here, into the middle of which Newton made a long insert, only then to decide to delete the whole thing with a consequence that has never appeared in print. It starts with a thought experiment in which the Earth is divided into two outer sectors pressing against the middle sector, and then separated and let fall. I'm going to quote only the insert and the conclusion. So quoting, "It is not legitimate to imagine that the gravitation of each of the two takes place toward another place distinct from the two bodies. For the imagined space is similar and does not have any specific point towards which gravitation takes place more than any other. If the whole Earth were moved out of its place, there's no doubt that its parts would even then gravitate toward its center and would not seek the middle, which is now put out of the center of its former place. For the properties and operations of bodies depend on the bodies and thus will not remain in spaces out of which bodies are moved, but will accompany bodies when they are transferred. Magnetic force follows a magnet, electric force follows ampere, centripetal force follows a planet. And similarly, the forces with which the bodies FH and HC fall towards each other accompany these bodies when they've been drawn apart. As long as the middle part HI is balanced by the contrary sections of the outermost parts, FH and IC, it yields to the weight of the part IC, the other part FH having been withdrawn. But if that part FH were moved further away and its action on the bulk HC ceased because the distance was too great, it should not be believed that the part HI would now yield more to the weight of IC and would flee indefinitely with a motion always accelerated. Perpetually accelerated motion in a straight line must by no means be granted to the forces of nature. That by the first law denied, the body HC will be at rest, and thus by falling towards the body FH when it is near, demonstrates its attraction. The parts therefore urge each other equally by their weights, that is, are urged toward each other equally as the third law requires, and thus if drawn apart from each other and let go, would fall toward each other's with velocities that would be reciprocally as the bodies. It's legitimate to test and observe all this in the magnet. Falling towards one another with velocities reciprocally as the bodies, that's the property, that's the main consequence of the third law of motion. So this is the verso side where it's showing Newton's long insert with deletions and revisions typical of his drafts. My point here is that Newton was struggling to express himself, introducing a long insert into the middle of a text in his amanuensis' hand in order to get something closer to what he wanted, and then giving up on the article entirely. This shows the page where the insert was to occur, marked in red, with Newton's numbers in the margins off by 1 due to an earlier slip. What's striking is that the text continues right on, showing that the whole thing was transcribed by Newton's amanuensis. Then before continuing to the next article, Newton modified it and added the insert on the verso side of the preceding sheet, only then to abandon the whole article and start all over with a variant of the initial claim. All this happened as the text was unfolding, not when Newton came back to it at a later point and decided to make changes. The new Article 23 replaces the deleted one, skipping all the explanation in it without abandoning its thought experiment. This thought experiment ended up not appearing in the first edition of the Principia, but stripped down, it did finally appear in the second in the Scholium to the Laws of Motion. Article 24 then asserts that the same forces tend towards celestial bodies. The first argument amounts to an inductive extrapolation from the terrestrial to the celestial. And the second corresponds closely to the argument given in Proposition 7 of the Principia, invoking as license the conclusion of Proposition 39. This was an early version of Proposition 69, the one cited as license for the second half of the numerator of the law of gravity in the Principia. Now, one might have thought that the conclusion of this article had already been reached back in Articles 20 and 21, but apparently not to Newton's satisfaction. Rather than concern ourselves with that, though, let's look at Proposition 39. I really wish Howard would be. This is one of his favorite propositions, but the original, the Principia version. I've included the scholium following the Proposition 39 because it shows Newton uncertain about how to justify the shift of forces toward bodies composed of forces toward the particles of matter forming them. The first thing to notice about the proposition itself is its use of the word pondus. This indicates it was written after Newton had chosen the word, and hence after Proposition 3 was attempted. A second thing to notice is that the reasoning here, just as in the Principia, proceeds from all bodies at any point responding to the attractive forces in the same way, regardless of their quantities of matter, and hence the forces varying as the quantities of matter in the bodies on which they act, to the conclusion that the attractive forces are proportional to the quantity of matter of the attracting bodies. And just as in the Principia, what licenses the inference is the third law of motion, within the proposition expressed by the phrase, the attractive forces ceteris paribus are as the attractions. So just as in the Principia, the second half of the numerator of Newton's law of gravity is being derived from the assumption that the third law of motion holds by virtue of what Howard called, quote, the speculative application of the third law to celestial forces. The one real difference is Article 21, which, recall, ends with a statement, in this way conceive that a simple operation arising from the two concurring natures of the two planets is exerted between them. A statement for which there is no counterpart in the Principia. An obvious question is how Newton came to have so much confidence in the third law of motion. Newton's action-reaction principle goes back to his student days, but the first place he invoked it publicly was in an illustrative problem in his lectures on algebra. In it, he uses algebra to derive the solution for the impact of perfectly elastic spheres that Huygens and Christopher Wren had published in 1669. Newton's two premises, however, are different from theirs. The third law and the claim that the relative velocity of separation is the same as the relative velocity of approach. The latter, of course, holds only for so-called perfectly elastic spheres, of which there are none in the world. The next place the third law appears is in the irregularly yielding media de motu tract that dates from before the initial version of Liber Primus. There it's followed by laws stating Newton's relativity and center of gravity principles, with the latter including the remark, this law and the two above mutually confirm each other. So at this juncture, Newton may have been thinking that these two principles from the earlier de motu tract had already committed him to the third law. But then he later came back and inserted the remark I've highlighted. In fact, this law is determined by definitions 12 and 14, insofar as the force exerted by a body to conserve its state would be the same as the force impressed on the other body changing its state. And the former force would be proportional to the change of state of the former, and the latter to the latter. Definition 14 is for impressed force, definition 12 is for inherent force, with the latter including the remark, it is proportional to the quantity of the body and is in fact exercised proportionately to the change of state. And insofar as it is exercised, it can be said to be the exercised force of the body. This insert suggests that he saw the third law as intrinsic to his conceptualization of inherent force, vis in situ. You don't have a copy of this slide. I want to make a minor point. You can see the law 3. When I say he inserted it, it wraps all the way around the arch. Okay? He inserted it at a later point. All this suggests that he was taking the impact of spheres to be the archetype of mutual interaction, with the question of which force is impressed on which body at impact purely a matter of point of view, insofar as, in the words of Article 21, impact does not involve two distinct operations, each body acting on the other, but a single operation between two bodies. But then the question is, what warrants his taking the third law to hold in the impact of real spheres and not just perfectly elastic ones? The answer lies in the experiment described in the scholium to the laws of motion in the Principia, where it's copied word for word from an expanded version of Liber Primus dating from later in 1685. Others before Newton had tried pendulum impact experiments to check the theoretical results for perfectly elastic bodies, but with results far less telling, if only because, unlike him, they had not introduced the corrections for the effects of air resistance schematized in his figure. Newton used 10-foot pendulums with spheres of different as well as equal sizes, quote, coming together from large distances, say of 8, 12, or 16 feet. Do try to picture two spheres coming together from 16 feet. The velocities of each body immediately before and after impact were inferred from the corrected values of the heights. Most important of all, Newton's version of the experiment included spheres that were not perfectly elastic, ones made of tightly wound wool, of steel, cork, and glass. His results for the first ratios shown in the slide were always close enough to 1 to confirm the conservation of linear momentum, and hence the third law of motion for a range of non-perfectly elastic spheres. The measured value for the other ratio turned out to depend on the material of the colliding spheres, with a roughly constant characteristic value for each material. Newton's 15 to 16 for glass, by the way, is virtually the same as the modern number. For those not familiar with how we do impact now, it's this. We go out and measure the coefficient of restitution for each kind of matter against matter, and that's the total theory we use, whether it's for a golf club, baseball bat, or anything else. Of course, the point here is Newton's conclusion. The third law of motion, insofar as it relates to impacts and reflections, is proved by this theory, which plainly agrees with experiment. It doesn't take much thought to realize that this is an even more demanding experiment than the two pendulum one I described before. Think of how difficult it is to have two spheres of different sizes approaching one another from 12 or 16 feet away and having to impact dead on the line between their centers. This experiment, too, required a great deal of time. So when did he do it? The manuscripts show only that it was done before the end of 1685. But already in early 1685, he had carried out the two pendulum experiment with 11-foot pendulums, and already in early 1685, he had concluded that Corollary 3, announcing the universal conservation of linear momentum, had been published. So I don't think it unreasonable, here's my phrasing, I don't think it unreasonable to propose that he carried out this experiment at more or less the same time as the other one, after the original draft of In Yielding Media, while he was in the course of developing the original version of Liber Primus. Let me go back to Liber Secundus. Just as in the Principia, the next step after establishing the law of gravity is to conclude that centripetal forces among the planets vary as the inverse square above their surfaces and linearly below, at least under plausible assumptions about how the density is distributed within them. Unlike the Principia, however, no numerical values for the relative masses of the planets are stated anywhere in Liber Secundus. I've highlighted one claim in this article because it never made it into any edition of the Principia. It has already been established that these forces arise from the universal nature of matter, and therefore the force of the whole globe is composed of the forces of all the particles of which it is made. I'll let you draw your own conclusion about whether Articles 20 through 24 have in fact established this. The next article introduces for the first time Newton's distinction between the absolute motive, and accelerative quantities of centripetal force, though notice that the original words were absolute, collective, and local, and that Newton replaced the latter two with motive and accelerative at a later time. We have here the first explicit statement of the law of gravity in Liber Secundus, a law giving the motive quantity of the force. The most important point, however, is that the, quote, the velocity with which the attractive globe will move in a given time towards the ether is determined by the accelerative quantity. The last sentence tells us why the threefold distinction is needed here. Quote, now that these things have been properly understood, it will be easy to determine the motions of celestial bodies among themselves. Article 27 then gives a long proof of the Copernican system totally different from the one in the Principia. It makes no mention of the center of gravity of the system, nor mention of motion of the sun. Instead, it argues that absent forces from outside the system, only the absolute force toward the sun can maintain the observed motions. The force toward the earth is far too small. Why Newton never included any version of this defense of Copernicanism in any edition of the Principia, and I think I can speak for Rob here as well, regard as an important question to which we do not yet have the answer. The first place Newton's threefold, again, this is a slide I didn't stick in for you. The first place Newton's threefold distinction among quantities of centripetal force is laid out formally is in a single folio in his hand shown here. I included it because it's in his handwriting. It too is typical of a Newton draft with revisions, often just changes in phrasing, almost before the ink is dry from the first draft. As noted earlier, this is the first manuscript we have from 1685 in which Newton employs the words mass and inertia. The most interesting point is the long insert in the definition of inherent force of matter. Quote, and the exercise of inherent force is resistance and impetus, which are distinct from one another in only one respect. It is resistance insofar as the body struggles against the impressed force, impetus insofar as the body, not easily yielding, endeavors to change the state of another body. Common folk, moreover, attribute resistance to bodies at rest and then impetus to those in motion, but motion and rest as commonly conceived are distinguished from one another only by point of view, nor are bodies truly at rest that are commonly considered at rest. Notice how reminiscent this is of the conception of mutual action in Article 21. The threefold distinction as Newton lays it out here expands significantly on Article 26. What are here defined are three quantities of force, with Newton then in inserts allowing them to be spoken of as three kinds of force. Notice too the caution at the end that he is here considering these forces not physically, but merely mathematically. That warning seems to me at some remove from his discussion of a single operation of mutual interaction in Article 21. I'm also struck by the point I've highlighted, quoting again, whence near the surface of the earth where accelerative gravity is the same in bodies universally, motive gravity or weight is as the body. But in receding further from the earth and ascending to regions where accelerative gravity comes to be less, weight will be correspondingly diminished and will always be as the body multiplied into the accelerative gravity. Here Newton has clearly realized a point that Craig Fox called attention to in a paper last summer, namely that a balance scale, unlike a spring scale, measures mass, not weight. I hope everybody sees that. The one other manuscript we have before April 1686 in the manuscript of Book 1 that went to London is a large fragment of the much expanded Liber Primus that postdates the Liber Secundus manuscript. This manuscript is the earliest place we have in which the definitions are followed by the scholium on space and time, and the statement of the 3 laws and 6 corollaries are followed by a scholium in which the experiment verifying the 3rd law is described. It's generally close to the text of the Principia, but not everywhere. The initial definition of quantity of matter in his amanuensis' hand was the one shown on the slide earlier. Newton first started to modify it, then deleted it, and drafted the one shown here on the verso side of the folio. This definition is followed by 2 that Newton decided not to include in the Principia. One for the axis and the other the center of matter, which we would now call the center of mass. I don't know why he decided to drop them at most a few weeks later. The threefold distinction is now formulated in 3 separate definitions, as it is in the Principia, and as there is formulated not as a distinction among 3 quantities, but among 3 measures of centripetal force. This is the first place we have where he speaks of centripetal forces as propagated from the center through the surrounding regions, or below that of a certain efficacy diffused from the center through each of the surrounding regions. As I said earlier, his speaking in this way seems to me full license for Howard's talk of an acceleration field, the anachronism of the world field notwithstanding. But the most important new point in my mind is the one I've highlighted. Motive force, quote, may always be known from the force equal and opposite to it that can prevent a body from falling. Although Newton doesn't say so, I take this remark as a concession that without recourse to the law of gravity, no phenomenon of motion in our solar system can determine the magnitude of the motive measure of the force acting on any body in it. But then, as he must have recognized, all he ever needed for anything he did in either Liber Secundus or in Book 3 was the accelerative measure. So let me summarize. The manuscript evidence not only supports Howard's conjecture that Newton developed the conception of forces of nature as necessarily forces of interaction, at the same time he was discovering the law of gravity. Let me just pause for a moment in case people haven't thought of this. No one before him proposed all forces of nature have to be forces of interaction. That was a very radical step. It indicates that his doing so dates from quite early, 1685, if not before. Second, the consideration driving both of these was the half of the numerator that did have full claim to having been derived from phenomena, celestial as well as terrestrial. The extraordinary aspect of gravity, its proportioning itself to the body on which it is acting. Newton was no less fixated on this aspect of gravity and its implications in 1685 than Einstein was 225 years later. Third, the sense in which 1685 was a year of gestation is that Newton developed over the course of that year an increasingly felicitous vocabulary as part of his effort to find a way of presenting the half of the numerator that he could not derive from phenomena. Fourth, the articles on the numerator in Liber Secundus show that Newton was perfectly aware throughout 1685 that in Euler's words from 67 years later, quote, it is still not decided by any single phenomenon that the attractive forces of heavenly bodies are proportional to their masses. And finally, when writing Book 3, Newton must have purposefully chosen to suppress this lacuna by inserting the claim that the 3rd law holds for celestial gravity in a parenthetical and a subordinate clause in a corollary to a proposition prior to the question of turn to the numerator. Coates's letter to him 26 years later could scarcely have surprised him. Now for the moment in this talk that I most wish Howard would hear. Howard spoke of the conception of a force of nature as a force of interaction characterized by law of interaction as metaphysics. use that word, trembling. All the manuscripts I presented so far with phrases like "it's reasonable also to grant" and "conceive that a simple operation arising from the conspiring nature of two planets" indicate that at the time it fell more into the realm of metaphysics than the realm of conclusions gathered from phenomena by induction. Newton, however, didn't stop here. After he completed Liber Secundus in late summer 1685, he returned to Liber Primus, adding some 40 new propositions. Among these were propositions 80 and 81 on the attraction toward spheres composed of particles that attract in proportions other than inverse square, and proposition 91 on attraction toward non-spherical bodies of revolution composed of inverse square attracting particles. Proposition 92 then announces an experiment that can determine the proportion for gravity toward individual particles of matter. The first step of such an experiment is to establish that attraction toward homogeneous spheres is inverse square. Then, as originally formulated, the next step is to verify with cylinders of various aspect ratios that attraction toward them is attraction toward their individual parts. Because he knew how weak gravitational forces are, Newton doesn't appear to have pursued such an experiment. But then in the summer of 1686, he learned from Halley of the French discovery that gravity is less at the equator than in Paris. This led him to add two corollaries on spheroids to Proposition 91 while Book 1 was in press, and then to introduce into Book 3 something that was totally absent in Liber Secundus, a theoretical relation between the degree of non-sphericity of the Earth and the variation of surface gravity with latitude. Judging from the fact that this is the only portion of the Principia that Newton rewrote not only in the second, but then again in the third edition, he was clearly hoping that these phenomena would establish empirically that terrestrial gravity is composed of inverse square attractions toward the individual particles of matter forming the Earth. From the 1730s until the 1850s, a lot of expeditions were carried out in an effort to show this, with some success, though less success than they were hoping for. But then in the mid-1840s, people began doing Cavendish-type experiments with different sizes and shapes of attracting bodies from the ones he had used. Cavendish himself had not varied either the masses or the distances between them in his measurement of the mean density of the Earth, and so his experiment did not begin to show that gravity is proportional to the mass of the attracting body. But there was enough variation of the attracting masses from one Cavendish-style experiment to another between the 1840s and 1890s to have shown this, even if nobody was intending to show it. At one time, I thought I was the one to have discovered when we finally had clear empirical evidence for the problematic half of Newton's Numerator. But then Chris Smink called my attention to this review article by Jonathan Zinnick. In it, he asked what evidence there was that gravity is proportional to the mass of the attracting body if the third law is not taken for granted. And his answer was this sequence of Cavendish-style measurements, including a pair employing respectively 154 and 100,000 kilogram attracting masses of lead. Do try to picture what 100,000 kilogram attracting mass of lead looks like in a laboratory. So ultimately, experiments along the line of the ones sketched by Newton in Proposition 92 did indeed fulfill his hope for an unimpeachable empirical basis for the second half of the Numerator, and therefore Howard's claim that it was largely metaphysics finally got resolved with empirical consideration. Thank you.